right, so in this set of notes, we are looking at inscribed polygons. In the last set of notes, we talked about inscribed angles, that being an angle whose vertex is on a circle and whose sides are chords, like what we see here in angle ADC or angle ABC. There are actually 4 inscribed angles here in this polygon. All right, so 2 definitions to start what we're doing in this section. An inscribed polygon is a polygon whose vertices all lie on the circle. And we can see the vertices A, B, C, and D all lie on this circle. A circumscribed circle is a circle with an inscribed polygon. So the circle here is circumscribing the inscribed polygon. So we could say this in 2 ways. I could say that polygon ABCD is inscribed in the circle, or I could say the circle circumscribes polygon ABCD. So a nice way to connect this to things we already know. An inscribed angle has a vertex on the circle. An inscribed polygon has vertices on the circle, which is why we use the same word, inscribed. Circumscribed, if we think about the word circumference, meaning the distance around an object, circumscribed circle indicates that the circle goes around the polygon, touching each of the vertices as it completes its path. So we've got a couple of theorems then here that are related to inscribed polygons or circumscribed circles. So with this case, we have the first theorem. If a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. So in this case, what that's saying is if triangle DEF is a right triangle, then segment EF is a diameter. So if a right triangle is inscribed in a circle, then the hypotenuse becomes a diameter. And what that would also mean, that would indicate here, since EF is the hypotenuse, since that's the hypotenuse, the angle at point D, angle EDF, that has to be the right angle. Remember, the right angle is always opposite the hypotenuse in a right triangle. Conversely, if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is the right angle. So in other words, if we see a triangle inscribed in a polygon, and we're given that one side is a diameter. So if triangle DEF is an inscribed polygon, if it's not inscribed, then this is not going to apply. And we're also given the segment EF is a diameter. If both of these things are given, so that and is important, then angle EDF is a right angle. Remember, that's always the angle opposite the diameter. And triangle EDF is a right triangle. So this works in both directions. Sometimes you'll be given that the inscribed triangle is a right triangle, and you'll have to conclude something about the diameter. Other times you'll be given an inscribed triangle and told it's a diameter, and you'll have to make the conclusion that you have a right angle, correctly identify the right angle, and identify that it's a right triangle. So it can go either direction here. Part of it's going to be given, the other part will be your conclusion. All right, so that takes care of triangles that are inscribed. This next theorem is related to quadrilaterals that are inscribed in a circle. So in this case, our theorem, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So if a quadrilateral, and this only applies to quadrilaterals, it does not apply to other polygons. If a quadrilateral is inscribed in a circle, then the opposite angles are supplements. So angle A and the opposite angle, remember that's the one it's not adjacent to, not consecutive with. Angle A and angle C are supplements. In case we've forgotten, that means the measure of angle A plus the measure of angle C must be 180 degrees. And angles B and D, the other pair of opposite angles, are supplements as well. So there, in that case, that would mean the measure of angle B plus the measure of angle D equals 180. So this theorem is biconditional like the last one. It has the if and only if in place, which means sometimes you'll be given a quadrilateral that's inscribed and you'll have to do something with the opposite angles being supplementary. Other times they'll tell you that the opposite angles are supplementary, and you'll have to be able to conclude that it must be an inscribed polygon. So in either case, we're going back to these two equations, keeping in mind that the angles involved each time are opposite one another in that quadrilateral. So let's look at a couple of examples then related to inscribed triangles or inscribed quadrilaterals. Our first example down here at the bottom of the page has an inscribed triangle. And we can see in this case that the triangle has one side that's a diameter. We know it's a diameter because it passes through the center. Now, if that's the case, if we have a triangle that's inscribed with one side being the diameter, then the side opposite that diameter must be the right angle. So in this case, 3x degrees must be 90 degrees. Has to be a right angle, which means, dividing both sides by 3, that x must equal 30. And that takes care of number 1. So some of the problems that will be given will be very brief. It's just simply a matter of, do you remember the theorem well enough to be able to apply it? All right, let's look at some examples then on the back page. We've got a couple more back there related to quadrilaterals. So in a quadrilateral, we know it can be inscribed as long as both pair of opposite angles are supplementary. So in this case, x and 85 must be supplements. So x plus 85 must equal 180. If we subtract 85 on both sides, then that's going to give us our value in this case for x. And that would be 95 for x. Likewise, if we look at the other pair of opposite angles, y and 80 must be supplements. So there they must total 180 degrees. Subtracting 80 from both sides produces y equals 100. So sometimes our solutions are going to be very brief and pretty direct. Other times there will be a little more algebra involved, and that's what we're going to see here in example 3. All right, so once again, we have a quadrilateral that's been inscribed in a circle, which means both pair of opposite angles must be supplements. So in this case, the measure of angle B, x plus 95, plus the measure of the opposite angle, 42y plus 1, must equal 180. Okay, so I'm going to combine what like terms I can. Let's see, that'll leave me with x plus 42y. 95 plus 1 produces plus 96 equals 180. I'm going to go ahead and move that 96 to the other side. So I'm going to take 180 minus 96 and get a value of 84 degrees there. Okay, so x plus 42y equals 84. There's nothing that I can do with that at the moment. So let's look at the other pair of opposite angles and see what that tells us. So here, C and angle A, those have to be supplements. So 2x plus 69 plus the opposite angle, 55y plus 1, must total 180. So let's follow the same steps we did before, combine our like terms. We have 2x plus 55y plus 69 plus 1 is 70 equals 180. Okay, like we did up above, I'm going to go ahead and subtract 70 on both sides to come up with that. Okay, so at this point I have two equations with two unknowns, what in algebra we would refer to as a system. So there's one, here's the other. Those two equations are what we have to work with together to find our solution. There's a couple of ways you can do that. You could solve one equation for either x or y and substitute that quantity into the other equation. Or we could use elimination if we could produce the same value but with, or the opposite coefficients. For example, here, if I could multiply this top equation by a -2, then that's going to produce opposite coefficients on x, and then I could add those two equations together. So that's an option as well. And that's going to eliminate the x and allow us to find y. That's the route I'm going to take here. I think that we have more comfort with solving for a variable and substituting, but there will be some instances where using elimination is going to be a quicker route, so I kind of want to use that here just to review it with you and nothing else. Like I said, you could use substitution. Either process is going to work. So I'm going to take these two equations and I'm going to write them down here again, just so that I have them together. All right, so as I said, I want to use elimination, and I'm going to do that by producing a coefficient of -2 here on this x term. And we do that by multiplying everything in the top equation by -2. So I'm going to multiply everything here by a -2. Remember that multiplication property of equality says that as long as you multiply both sides of the equation by the same value, that you're not upsetting the balance of that equation at all. You're still going to have two equal quantities. Okay, so when I do that, I get an equation of, let's see, -2 times x, and I'm going to go ahead and write it below this one. -2 times 42 is a -84y equals 84 times -2 on the other side gives us a value of -168. Okay, so for now, I'm going to ignore this equation that I have up above. It was useful to me, but at this point, I no longer need it. So I can see in these two equations, now I have two x values that have opposite coefficients, which means if I were to add these two equations together, the 2 plus the -2 is going to produce a coefficient of 0, which means that term is going to drop out. So I'm going to go ahead and add these two equations together. So I'm going to add on the left side and I'm going to add on the right side. 2 plus -2 is going to produce a 0 in this position. 55 plus a -84, be careful with that negative there, even though we read it as a minus, we're understanding it to be a -84y, produces a -29y. And on the right side, 110 minus 168 or plus -168 gives us a value of -58. So automatically I've eliminated x and it's down to a very simple equation to solve for y. Divide both sides by that -29, we get y equals 2. And that's one of our two solutions. We also have to find x. Now, when it comes to finding the value of x, we have any number of places you may substitute that back in. You can take this value of 2 and substitute it here into this equation and find x. You could substitute it here to find x. You could substitute it there. Anywhere on any of these equations where we have a y, I can substitute a 2 in order to find x. And I'm going to do that using this equation up here, simply because x doesn't have a coefficient. Not to say I couldn't use any of the other ones, I'm just choosing to use that one. So using that equation then, I get x plus 42 times y, which is 2, equals 84. So x plus 84 equals 84. Subtract 84 from both sides and we get x equals 0. And those become our solutions. Now you could go back and substitute to check your work, In this case, if I let x equal 0, then this angle becomes 95 degrees. This one here, where x is 0, then C has a measure of 69 degrees. Using our value of y of 2, 42 times 2 produces 84, plus 1 is 85. And in this case, 55 times 2 gives us 110, plus 1 is 111. Now what should happen is that the opposite angles are supplements. So in this case, 95 plus 85 is in fact 180, so that works out well. Here, if we check again, 69 plus 111 is also 180, which indicates that our two solutions are correct. And that would be how we worked with inscribed polygons.